Hi everyone. In this video we are going to talk about remainder theorem. The remainder theorem says that if we have a polynomial p of x, and if it is divided by another polynomial which is like this, then from here we get a remainder the remainder will be equal to p of c. And what is that c? This is this c, whatever is the real number c. So p of c will be the remainder when a division takes place like this, or when p of x is divided by x minus c. So now we have to see how this theorem can be proved, right? Now before I go into the formal proof, I want to do couple of divisions here, normal plain division, to build a couple of intuition here, right? First we need to see how the division works, and then we'll go into the formal proof. So let's take an example first, an example of a division. So suppose I'm going to do this division. Suppose you have a polynomial p of x which is suppose 3x cubed. So our original polynomial is 3x cubed plus 2x squared plus 5x plus 1, right? And we're going to divide that by another polynomial which is a second degree polynomial x squared plus 1. So our original polynomial is a third degree polynomial. It is 3x cubed plus 2x squared plus 5x plus 1. We're going to divide that by a second degree polynomial. Now let's do the division. So x squared goes 3x times into 3x cubed. So that would be 3x cubed plus 1 times 3x, that would be 3x. So I'm going to write it here. I'm going to align it along with the x term of the original polynomial, or of the dividend. And then we need to change the sign, so it becomes negative, and then this is going to cancel out each other, and then here we are going to be left with 2x, positive 2x plus 1. And also we have the 2x squared here. So we have the 2x squared here, and then positive 2x here, and then plus 1. Now x squared goes 2 times into 2x squared, so in the quotient I write plus 2, then it will be 2x squared, and then 1 times 2, that would be 2, right? So I write it like that, and then again we're going to change the sign, and this is going to cancel each other, and we're going to be left with positive 2x minus 1, right? Now if you look at the divisor, which is x squared, and now we are left with a term here which has only a 2x. So the power of x here is 1, but the power of x in the divisor is 2. So this division pretty much has ended. It cannot continue anymore. Now because whatever we are left with, its degree is less than the divisor, so we cannot continue the division anymore. So essentially this is our remainder. So I highlight that with a red box here. So this is our remainder, right? Let me say remainder. So this is our remainder. Alright, now let's do another division. So let's take another example. Suppose this time we are again going to use the same polynomial which is 3x cubed plus 2x squared plus 5x plus 1. But this time we are going to divide the polynomial by a linear polynomial which is, let's say, x plus 1. Here the degree of the divisor is 1. Previous example, the degree of the divisor was 2, but now we are using a divisor where the degree is 1, because here the power of x is 1, right? So let's continue this division and let's see what happens. So x goes 3x squared times into 3x cubed. So in quotient I write 3x squared, and then here it would be 3x cubed, and then 1 times 3x squared, that would be 3x squared. and then we need to change the sign and then do the algebraic addition, and these two will cancel out each other and we will be left with negative x squared here and then positive 5x and plus 1. Now x goes negative x times into negative x squared. So in the quotient I put negative x and then negative x times x, that becomes negative x squared, and then negative x times 1, that is again negative x, and again we do the same thing here. The sign will change, so this becomes positive, this becomes positive, and then this is going to cancel out each other and we are going to be left with 5x and one more x, that would be 6x. So we have 6x here plus 1, and then let me scroll down a little bit, and then x of the divisor, he goes 6 times into 6x. So here in the quotient I'm going to say positive 6, then 6 times x, that is 6x, and then 6 times 1, that will be 6, right? And again we're going to change the sign. This becomes negative, this becomes negative, and this is going to cancel out each other, and then we are going to be left with a negative 5 here, right? Now can the division continue anymore? No, because we don't have any x term in whatever the number we are left with. Now we are left with a negative 5 where the power of x is 0. There is no x term, that means the power of x is 0, but the divisor has an x term where the power of x is 1. So this division cannot continue anymore, and now we have found the remainder of this division, right? This is the remainder in this case. Now if you look at the remainder that we obtained from both these divisions, I'm going to scroll up a little bit. You will notice one thing, that the degree of the remainder is at least 1 less than the degree of the divisor. That is the most important concept we all need to understand here, that the degree of the remainder could be a polynomial of x, right? Like in the first division here, that the degree of the polynomial is 1 right here, whereas the divisor has a degree of 2. On the second example, degree of the remainder is 0, whereas the degree of the divisor is 1. So you always see that the degree of the remainder is at least 1 less than the degree of the divisor. That is the most important concept we need to understand here. Now if we have understood that much, then let's move into the formal proof of this theorem. So far we have seen that the degree of the remainder is at least 1 less than the degree of the divisor. Now let's draw a general picture about division, about the dividend and the divisor and the quotient and the remainder. So the general picture of a division is kind of like this. Say suppose our dividend is p of x. If the dividend is p of x, then we can say that is equal to our divisor, let's say it is d of x. Suppose this is a polynomial which is the divisor, times the quotient, let's say q of x, plus the remainder, and we want to say r of x, right? Let's say r of x, that's the remainder. So this is the general picture of a division where you have the dividend as the original polynomial which is p of x. This is the dividend. So this is the dividend. Let me write it down here. So this is the dividend, and then here this is the divisor. This is the divisor, and this is the quotient, and this is the remainder. All right. Now, so far we have seen that the degree of the remainder is at least 1 less than the degree of the divisor. Now, if I slightly modify this picture into something like this, say suppose we have, let's say, suppose we have a polynomial which is p of x, and it is being divided by a polynomial which is like this. Instead of d of x, I want to write this. So a polynomial of x is being divided by x minus c, giving a quotient of q of x and giving a remainder. Now think about a remainder this time. When the degree of the divisor itself is 1, meaning the degree of x or the power of x in the divisor is 1, then what would be the power of x in the remainder? It must be at least 1 less, right? So if the degree of the divisor is 1, then the degree of the remainder will be 0, right? It has to be at least 1 less. So the degree of the remainder is 0. That means the remainder is a constant term. There is no x term there. The power of x is 0. That means the remainder is a constant term. So instead of writing r of x, I am going to write just a small lowercase r, because the remainder is a constant term. There is no x term in the remainder, since the degree of the divisor is just 1, and the degree of the remainder has to be 0. It cannot be 1, it has to be 0, because the degree of the remainder is at least 1 less than the degree of the divisor. So for this particular division, if we divide p of x by x minus c, we are going to get a constant term in the remainder. There will be no x term in the remainder. It will be a constant term, right? So now from here we can say, okay, so what is our remainder then? So from here we can say r is equal to p of x minus x minus c times q of x. So r will be equal to p of x minus c times q of x, right? Now, in this general form, we don't know what is the value of q of x. So somehow I want to get rid of this portion, because I am trying to come up with a formula. I want to get rid of this portion. Now what is the easiest way to get rid of it? Well, if I substitute x by c, then this portion right here, the first portion right here, will become 0. So I am going to now substitute x by c. So if we substitute x by c, then we can say that our remainder will be equal to, now wherever we have x, I am going to use c, because we are substituting x by c. And then here it will be c minus c, because this x is now c, and then times q of c. And I don't care what is the value of q of c, because this entire term right here, this term is becoming 0. This is now becoming 0, because c minus c, that's 0, right? So here we can say, okay, so this is equal to p of c minus 0 times q of c, which essentially means p of c minus 0, that is equal to p of c. All right. So finally, let me write down the picture. So the remainder is now equal to p of c. I'm going to use a different color. So if p of x is divided by a linear polynomial which looks like this, x minus c, then we get a remainder. Which is equal to p of c, right? Now let's take an example to see how it works out. So suppose we have a polynomial. So we are going to take an example. Suppose we have a polynomial p of x equals let's say x squared minus 3x plus 10, for example, right? So this is our polynomial, and we are going to divide that by, let's say, x minus 1, right? So we are going to divide that by x minus 1. So the division will be on x minus. All right. Now, if you look at this picture, right here, where we say x minus c, right? and here we have x minus 1. So this 1 corresponds to the c, as in our theory. In our theory, we say that if we divide the polynomial by x minus c, then the remainder is p of c. So in this case, this 1 is equivalent to the c. So what would be the remainder then? Here the remainder will be, I'm going to write it like this, remainder will be p of, instead of c, I am to say 1, because the 1 right here, the 1 right here is equivalent to the c in our theory, right? So in this case, if we divide p of x by x minus 1, the remainder will be p of 1. So now let's evaluate the value of p of 1, right? Let me use the yellow color here. So p of 1 will be, we are going to put 1 in place of x. So instead of x squared, it becomes 1 squared minus 3 times x, which is, I would say, 3 times 1, and then plus 10. So this is equal to 1 minus 3 plus 10, that is 11 minus 3, which is equal to 8. So if x squared minus 3x plus 10 is divided by x minus 1, the remainder will be 8. Now, can we have a quick look, or can we do a quick division? Let's do a quick division here. Suppose we are going to do this division, right? X squared minus 3x plus 10. Let's quickly do the division and see how that works out. And we're going to divide that by x minus 1. That's our divisor. So x goes x times into x squared. So in the quotient I write x, then this becomes x squared minus 1 times x, that is x. And then the sign will change. So this becomes negative, this becomes positive. This is going to cancel out each other. And we're going to be left with negative 2x plus 10. And x goes negative 2 times into negative 2x. So that is negative 2x. And then negative 1 times negative 2, that's positive 2. And again the sign will change. This becomes plus, this becomes minus. Then this is going to cancel out each other. And here we are going to be left with 10 minus 2, that is 8. So that is our remainder, and that's exactly equal to the remainder that we got by using the theory, right? So we have proved that yes, the theory is working, right? Now let's take another example. We'll take another small example. Suppose this time our p of x is, so this is another example, and for the previous one I should have said this is an example, right? So this is an example. All right, so on the second example, let's say suppose we have p of x equal to the same, we can take the same polynomial, right? Let's say the same polynomial, x squared minus 3x plus 10. And this time we are going to divide that by, let's say, x plus 1. So if we divide it by x plus 1, what would be the remainder? That is the question, right? So if we divide by x plus 1, what is the remainder? Now this x plus 1 somehow needs to be converted into the form that will look like x minus c, because see, in our theory we have the form x minus c. So somehow we have to convert our divisor into a form like this, x minus c, and then only we can directly use the theorem, right? So let's try to convert this into that type of a form. Let's say we are going to convert it into a x minus c form. So x plus 1 can also be written, it can be written as x minus negative 1. Think about it. If I convert this x plus 1 into a form like this, then this is essentially the c as we have seen in our theorem, where x minus c is the divisor. Now here our divisor was x plus 1, but we have converted it into a form which kind of looks like x minus c. So this is our c. This negative 1 is actually the c as in the theorem, right? So then now rest of it is easy. So what would be the remainder? Well, our remainder will be equal to p of c. And p of c means, in this case, what is our c? That is negative 1. So p of negative 1. So that is our remainder. Now let's evaluate that. So our polynomial is x squared minus 3x plus 10. So in place of x squared, I am going to write negative 1 squared Then minus 3 times x. For x I'm going to write negative 1 and plus 10. And this is equal to negative 1 squared would be positive 1. Then negative 3 times negative 1 would be positive 3. And then plus 10. And this turns out to be positive 14. So that is our answer. That is the remainder. When x squared minus 3x plus 10 is divided by x plus 1, we are going to get a remainder of 14. And you can try the regular division to prove that yes, it is actually going to become 14. You can try that. It's easy. And this brings us to the end of this video. Hope everything made sense. Thank you for watching. See you in the next video.